Great. So hopefully everyone should be coming in now. Once it starts doing its thing. There we go. Great. Thank you to everyone who's already here. I'm just going to keep letting people in. I think in the interest of time, because we've got a lot of content to get through today, we'll probably kick off and I'll just keep adding people to the webinar as we go. So yeah, good morning everyone. Welcome to today's REWIRE webinar. For those of you that don't know me, my name is Alex Oliver. I'm the partnerships lead for the REWIRE Innovation and Knowledge Centre. This is the fourth of our webinars that we've run since sort of midpoint this year, which should be a really interesting topic for everyone. Really focusing on power electronics and gate dielectrics and new techniques for that. So before I hand over to our group of presenters for today, I will just quickly introduce them. So we're joined by Dr. Arne Benjamin Renz, Dr. Sami Bolat, and Dr. Michael Powell from the University of Warwick, Hitachi Energy and Oxford Instruments Plasma Technology, respectively. So I'll just introduce them all quickly now. So Dr. Arne Benjamin Renz is an assistant professor and a leading researcher in silicon carbide power electronic interfaces at the University of Warwick School of Engineering. His research is focused on developing and commercializing novel ways of improving the power semiconductor interfaces that silicon carbide forms with oxides and metals for applications including automotive, renewables, and radiation-sensitive environments. Dr. Sami Bolat is the Senior R&D Engineer at Hitachi Energy with over 10 years of research experience in thin film electronics, microelectronics, and optoelectronics. Currently working on industrial R&D relating to wide bandgap power semiconductors, primarily on silicon carbide. Sami has published over 20 papers in prestigious journals such as Nature Comms and Advanced Electronic Materials, and has been recognized with several national and international awards for contributions in the field of electronic devices. Finally, Dr. Michael Powell is an applications development team lead focused on deposition at Oxford Instruments Plasma Technologies. He's been working there for 7 years, bringing new technologies and processes to market, including OIPT's first purpose-designed and engineered production ALD system called AtomFab. Michael is highly experienced in plasma-enhanced ALD processing of materials for semiconductor processing, with current focuses on silicon carbide, gallium nitride, and quantum applications for ALD processors. And he has 35 peer-reviewed publications and over 4,000 citations. So that was a mouthful. So at that point, I will actually, before I hand over to our presenters, if you do have any questions throughout, please feel free to add them into the chat and the Q&A. I'll be monitoring those. But without further ado, I'm going to start sharing my slides and also make sure that I then go on mute and hand over to Ben to kick off. Let me just make sure I've got on the right view. Is that working for you?
I think that's the right one, yeah.
Yeah, let me just move that around. There we go.
Perfect. Yeah, thank you. Thanks very much, Alex, and thank you everybody for attending today's webinar. I mean, this is quite an exciting opportunity, certainly for not only myself but also Michael and Sami, and I'm very grateful that they were willing to contribute to this webinar. Yes, next slide, please, Alex. So I've broken down the session into basically 3 parts. I'll give a very brief introduction on what we're doing, what we're collaborating on, and then I'll hand over to Michael Powell from Oxford Instruments Plasma Technology, who's gonna talk about the opportunities and products and technologies that they offer in the field of semiconductor surface engineering. I'll let Michael elaborate on that, and then Sami will talk about silicon carbide power MOSFETs and the developments that Hitachi Energy have carried out on the gate oxide front, and then I'll finish this off hopefully on time, and I'll talk about the project that the three entities here are collaborating on. Next slide, please, Alec. Right, just a quick introduction on how we got to work together, because I think this is actually a good example of how academia and industry can collaborate and have a real impact on the industry. So in 2017, basically, at Warwick, we began doing fundamental research into new silicon carbide interfaces. We did some of that on Schottky interfaces, but the most dominant and most impactful research has been done on the MOS interface, so the interface that silicon carbide forms with the oxide, especially very relevant for silicon carbide MOSFETs like FETs in the industry. Yes, the next, yeah, and then it took some time basically to develop the processes, and then actually we published the PhD findings on deposited oxides in a journal paper. The next one, Alex, please. And then that led to a feasibility study with Oxford Instrument plasma technology, where we basically thought, well, what could a potential improvement in the work that we've shown, how would that translate into device resistance? And we found that it could potentially reduce the device resistance by 10%, reducing chip cost by 5%, which is very relevant. Then we published our initial findings in an international trade magazine, and international companies picked up this method. And because both Oxford Instruments, obviously, and Hitachi Energy had independently beforehand already done research on developing gate oxide technologies, either on a different materials platform. I think it's fair to say that Oxford Instrument plasma technology have had a long body of knowledge and it's established a strong presence in the field of gallium nitride deposition of oxides, and Hitachi Energy have also done that. So this led then basically to an award of a £1 million Innovate UK Inno-Swiss research project, in which we are now looking to commercialize the process. And with that, I think I would like then to hand over to Michael.
Thank you very much, Ben. Morning, everyone. So I'm Michael Powell, and I'm from Oxford Instruments Plasma Technology. What I'll do first off is take you through Oxford Instruments as the group. So next slide, please, Alex. So the Oxford Instruments group is quite a wide-ranging group. As I say, I'm from Plasma Technology, and we are dealing with deposition and etch processes for adding and removing thin layers of films. But we also have nanoanalysis, Asylum, VTech, who fall under our analytical wing. So they do EDS, EBSD, AFM, Raman, and then we have the more magnetic parts. So magnetic resonance and X-ray technology. And then we got Andor, who do high resolution films. So many of you may have seen the Oxford Instruments logo, and that's why we're so commonly seen across universities and across different industries, because we do have a very wide range of different groups. Next slide, please. So within those groups, here's what we cover. We're doing analytics with electron microscopy, we do atomic force microscopy, and we do benchtop NMR, 3D Raman and correlative microscopes, scientific cameras, nano indentation, and then we get to where plasma sits, which is compound semiconductors, deposition equipment and etch, and solutions and recipes. And then we got X-ray as well. So we are a very wide-ranging group. And within that, we like to do a lot of R&D. So we like to stay close to our university customers, as well as looking at how we can get the solutions out to the wider market. And that's the bridge we try to gap within plasma itself. Next slide, please. And just to give a flavour of where, as a group, we sit with our research and development portfolio, we look across a very wide range of different scientific applications, ranging from advanced energies, advanced materials even, energy and environment, semiconductor and IT, quantum, fundamental research, and health and life care science. And within that, what we are trying to deliver is benefits for people and the companies that we work with. So we're always looking for what is the value add that we can deliver? How do we better use what we have? How can we drive the next generation of materials? How can we do better for the environment and the communities we work with? Next slide, please. This brings us on to plasma. So plasma technology is the division that I work within. We are based in Bristol. We have very recently moved into a brand new factory where we've invested over 100 million so that we can bring our R&D solutions to the market. This means that we can accelerate our R&D. We have a much greater clean room facility at this new factory than we did at our old factory. And it means that we are able to really address the challenges that we have within dep and etch and bring new processes to high volume manufacturing. So that is our ambition, is to take from research and development through to high volume manufacturing and deliver solutions that benefit the market. And that's why we were so interested in the REWIRE project itself, because it's really living the ideals that we want to have. It says, what are our technologies? How do they interface with the silicon carbide market? How can we show that we actually deliver a benefit to that market? And this is what we're trying to do with that facility.
Right.
Yes, next slide, please. So what we see as our critical markets are where plasma really gives a benefit. So all of our technologies are based on plasma. They're based on the fourth state of matter. And it's how can we use plasma to benefit critical markets. And within that, we've found that compound semiconductors is a market where plasma really can deliver benefits. So within that, you've got things like silicon carbide and gallium nitride. So the power and RF markets that go all the way from drivetrains in cars to renewable energy to high-speed communications to data centers. We feel that plasma can really deliver a benefit because it enables you to deposit materials with high quality at high speed with low temperature. You can also do plasma pretreatments, which means that you can make the surface of a material ready for either the etch or the dep that you want to do. We've also got quantum, so that's more of an R&D market for us rather than a high volume manufacturing market, but that is somewhere where we can really see a benefit, again, of using plasma technologies. There's augmented reality, which is looking at the headsets that you would want to have 3D vision for, things like Meta's headset. There's 3D sensing. So everyone's now aware that you can unlock a smartphone just using your face, and it's the lasers behind that actually enable you to do that technology that we have solutions for. And then there's data centers. So we've got indium phosphide and gallium arsenide there, but actually gallium nitride is really feeding into data centers now with the AI boom, because you need a very efficient way of transferring the data at very high processing speeds. So these are our overall markets, and silicon carbide, as you can see, is a really critical market for us. So again, why we were so interested in being in the REWIRE project itself. Next slide, please. And within this, where do we sit with our technologies? So our technologies are all based around either adding or removing materials and being able to do that at speed with control. So on the etch side, we are primarily based on ICP and reactive ion etching. On the deposition side, we have some ICP technology. We also use capacitively coupled plasmas as well. And then in between, it's how do you get the interface correct? So what can you do in order to ensure that the material is ready to be processed? Can you get back to a high quality interface before you do a dep or an etch? And how do you control things? So we all come back to control in the end. Next slide, please. And to give a flavor of where our technologies sit, so we have a broad range of technologies for both dep and etch. So I'll go through the deposition first. And what we have with all these technologies, you're always competing with how much can you control what you're putting down or removing, and how fast can you do it. So you can see on this graph, we have control in the bottom left-hand corner, and we have rate in the top right-hand corner. And especially for dep, control really does correspond to how slow your rate is. So with atomic layer deposition, you can do very high control, so very, very high quality materials with really good conformality, but you do have an impact on how fast you can do it. What we've been doing with our ALD techniques is improving the speed so that you can have a higher rate whilst not sacrificing on the quality, so you can still have the control. But if you wanted really fast rate, you would go towards our CVD side. Chemical vapor deposition is a very fast rate process. You know, you can get with plasma enhanced CVD, you can get thousands of nanometers a minute. You'll never get that in ALD, but in ALD we can give you processes that can be hundreds of nanometers an hour, so you still can get throughput, but that means you get the control, so you're able to better control. Next slide, please. And on the etch side, again, it's control versus rate. So what we have here are a variety of technologies that allow us to control or how high your selectivity is for what you are etching away. And then on the other side, it's rate, and we've also got smoothness. So when you're doing a plasma technique, you'll often find that what you get at the end is a rough surface. Now, if you want more smoothness, you can go over to atomic layer etch rather than a standard etch. And then on the other side, it's the rates and it's the selectivity. And these various technologies allow you to play between smoothness, control, and rate. Next slide, please. So if we come over to, or if you just go through these until we have them all on, please. Thank you very much. If you go through to our silicon carbide market and where we can show how our technologies can interface with this, we have a wide range of different technologies that we can leverage to improve the quality of a silicon carbide device. So, you know, it's everything from the initial silicon carbide layer right at the bottom, where we got a plasma polish process that means you can actually, rather than having to use the CMP process, you can use a plasma process to get the same kind of control on the surface, all the way through to the gate oxides deposition. And we have a range of technologies that allow you to look at each individual layer and have an ability to control each individual layer. And then, you know, if we go back to the other divisions of OI, we can use Raman and we can use the electron backscattering diffraction to actually tell you about the quality of the initial silicon carbide as well. So we can go through the entire methodology of producing the silicon carbide device, and we have a solution for each layer. Next slide, please. So that was quite a quick overview of where we sit as Oxford Instruments itself, and specifically plasma technology. But where we were really brought into the project was to talk about atomic layer deposition. So within silicon carbide, for a long time, it's been a thermal oxide route that has delivered the gate dielectric, and that has some drawbacks in terms of carbon at the interface and in terms of what that means for the quality of the device and the switching speed of the device and how much you can actually put through the device before it breaks down. If we switch over to atomic layer deposition, we have an ability to deposit a gate oxide and to reduce some of those contamination and some of those species that cause issues at the interface, because we aren't generating so much carbon there. And within our portfolio, we have two systems that allow us to develop ALD for R&D applications and HVM applications. They're based on a broadly similar level of technology as well. So if we generate something on our Plasma Pro ASP platform, we can actually transition it to high volume manufacturing quite quickly, because we're not talking about a fundamentally different plasma source. We're not talking about a fundamentally different way of depositing the material. What we're talking about is taking something that works well at an R&D level and making it applicable for high volume manufacturing, so it has the right certification, and then we can show the CPK and the marathon trials that will give you the long-term control over that as well. Next slide, please. And to briefly touch on what we can do with atomic layer deposition itself. So within the project, we had quite a broad remit, but what now seems to be shown to be the best material for silicon carbide at the interface is silicon oxide. So we've developed a silicon oxide ALD process that is high rate but high quality. So this we can do 100 to 150 nanometers an hour and deposit, as you can see here, with high conformality. So we can get above 95% conformality on a 10-to-1 aspect ratio. And when you look at the silicon carbide devices and where we're going with the MOSFETs, this is giving you quite a good level of control for this film so that you can have a gate oxide that really goes across the entire structure and deposits with high quality. So the way we measure quality is looking at thickness uniformity and looking at RI control. So on the thickness uniformity, you can see on a 200 mil wafer here, we can achieve 1.5% quality of thickness. And the way we define uniformity is you take your max minus your min and you divide by 2 times your average. So it's a 3 sigma kind of approach. So if you were to give this as a 1 sigma, it would be below 1% as well. And on the RI, you can see we've got a good level of control of the RI. We've got an average RI of 1.46, and you can see that that average RI is not changing much across the wafer either. So coupling those two things together with conformality means we have really good control of this silicon oxide, and we can really deposit this at speed as well on large substrates. So we'd have a good solution for bringing atomic layer deposition to the silicon carbide market. Next slide, please. And then to briefly touch on a new material we're bringing in for high volume manufacturing purposes. Now, this is less to do with silicon carbide gate oxides, but more as a top-up material, which is silicon nitride. So silicon nitride is one of those materials that's very, very challenging to deposit by thermal ALD routes. You don't have very many good co-reactants to go with your silicon precursor. And what we've developed is a low temperature plasma route that gives really good quality and really good control again. So here, nitrides are always a bit more challenging than oxides to get really, really good uniformity on, but we can get sub 4% on a 200 mil wafer, and we're getting control on the RI as well. So the RI is quite fixed for silicon nitride in ALD. 1.92, 1.93 is quite typical for RIs for silicon nitride. You can change the RI and CVD, but what you're actually doing is playing between the silicon and nitrogen ratios in the material. So for this is a stoichiometric silicon nitride film, and it's giving a stoichiometric silicon nitride RI value. And if we go to the next slide, we have also been able to show that the choice of precursor is really key. I can't give any details away about the precursor, but by changing our precursor, we were able to both increase our throughput and really, really improve the quality of the material. So quality of the material shown here on the left-hand graph, where we're doing a wet etch rate in buffered HF. So we've got a 10-to-1 buffered HF, and we refer that to a thermal oxide wafer to allow us to understand how quickly we are etching through the material. And the lower the etch rate, the higher the quality, the higher the density. And you can see with our highest rate process, we actually have our lowest etch rate. So we've got an etch rate of about 4 nanometers a minute for that film. But we are able to do about a 14 times increase on our standard ICP ALD. And this is bringing silicon nitride really into the ability to have a high volume manufacturing ALD route for silicon nitride. And we've modeled this on a 20 nanometer film, but we can do over 6,000 wafers a month if we do a 20 nanometer film of silicon nitride. So this is our portfolio. This is what we are really interested in doing. Can we bring an etch or a dep technique to a critical market that really delivers a benefit for that market, where we can leverage the power of plasma? And with that, Ben, I think we're handing over to Sami next.
Yeah. Your turn, Sami.
Yep, thank you very much. So Sami Bolat, as mentioned, I'm a senior R&D engineer at the Hitachi Energy Semiconductor side. We can move to the next slide. I'll be talking briefly about our company and the application areas of power semiconductors where we have our products. Then I will make a quick introduction into the silicon carbide power MOSFETs, where they are industrially used today, and then briefly touch upon the oxide silicon carbide interface properties. Then we'll make the bridge to Ben to give us the details about the technical developments that we are achieving in the InnoGate project. So Hitachi Energy, our company, is a global leader in the electrification business, where we have a majority of our products in the power grids. And the motto of the company is to advance a sustainable energy future for all, because these fields require really demanding development and demanding business interaction with several customers, governments, and so it is impossible to achieve everything as a single company or as a single team. But our company is doing its bit by driving the transformation on this field to advance a sustainable energy future for all. If you go to the next slide, I'll give some numbers about our company. So we are a quite multinational company with the employee numbers today actually over 50,000 employees, nationalities ranging from all across the world, 150 nationalities. The company has its presence at across 60 countries. And we have 5 business units: grid automation, integration, high voltage products, service, and transformers. Where we have the semiconductors business unit is in the grid integration. If we go to the next slide, I'll tell you a bit about the history of our company with the power semiconductors. So our history started with the power semiconductors over a century ago with our ancestor company, Brown Bowery, developing the mercury arc rectifiers, and then these ones found their applications in the trains in Germany. Later on, the company continued focusing on the bipolar devices with the development of the germanium diodes. But then, of course, 10 years later, the one that found the application in the field was the silicon diodes again. And then our location where we are today developing and producing the power semiconductor products is Landsburg. This was basically integrated almost 45 years ago. And for the next 15 years, the company, our units focused on producing bipolar products only. But then in 1997, we developed our so-called unicorn product, the stack pack modules, and then we continued also expanding the business with the BIMOS technologies. Then what relates us to the silicon carbide of today was the e-mobility product launch in 2019. That is our road pack module. And later on, we also expanded our line with a e-mobility silicon carbide module manufacturing line. And today, our business is expanding itself for the silicon carbide from e-mobility to even higher voltage volumes. If you go to the next slides, where we find the applications of the power semiconductors, our marketing department actually has a very nice saying for the power semiconductors. They call them as the silent superheroes of our daily lives. We use these modules, these products, basically everywhere in our daily life, from the generation of our electricity. In the next slide, we see that they are also used in the consumption level. For today's presentation, what is interesting is, of course, the road pack that we will see in the next slide. If we can go to the next slide. Yeah, exactly. So we have our product, the road pack, which was qualified using several chipsets from different vendors. And these modules respond to the needs of the e-mobility, basically for everything that is with wheels. This is how we define e-mobility today. It's not just the cars, but everything that has wheels and that we can drive on them. And in terms of reliability, performance, here you see the numbers. I'm not going to go too much into them, but the product is basically able to offer what the e-mobility market needs by its own means. What is inside of this road pack is silicon carbide power MOSFETs. If we can go to the next slide, I will basically mention how the silicon carbide power MOSFETs came into the market. So the first adapters of the silicon carbide was the Tesla early in 2014, where they used some discrete silicon carbide chipsets in the modules for the electric cars. And this actually boosted the technology development for the silicon carbide power MOSFETs for the e-mobility market. And today, and here you see only 3 car manufacturers, but it's now everywhere. Almost all the car manufacturers today use silicon carbide power MOSFET based modules to offer efficient energy conversion. And as Hitachi Energy, we have our products at the moment for the road pack and for the limb pack. The targeted applications do not limit themselves into only e-mobility. We want to go all above to the grid integration levels, so to ultra high voltage levels as well. At the moment, our products are road pack and limb pack, mostly for the e-mobility as well as for the railway traction inverter applications. So the silicon carbide power MOSFETs, yes, they are industrially applicable today and they are kind of everywhere for the e-mobility, but what is really missing is the saying that we have reached the final performance of these devices. In the next slide, I will briefly mention an important parameter about the silicon carbide power MOSFETs for the low voltage applications, mostly the channel resistance that is dominating the on-state resistance of these devices. And we know that the efficient power transistors require minimized on-state resistance. Of course, there are always engineering trades-off, which we are not going into the detail in this webinar. But the channel resistance is basically dominating the on resistance for the low voltage applications. And in today's world, we have the thermal grown silicon dioxide as industrially adapted gate oxide for the silicon carbide power MOSFETs. So if you take a look at the channel resistance in this formula, we can see that the oxide capacitance and the mobility, field effect mobility, are inversely related to the channel resistance that we get in a device. And this field effect mobility is something that is directly related to the interface between the dielectric and the semiconductor. In the next slide, I will touch upon this a bit. So silicon carbide, it is really good material in the sense that we can easily grow the thermal oxide on top of it. This is similar to the silicon. That's why among the wide bandgap materials, it also stood out as an industrially adapted choice for the power electronics. But the main difference is we have a wider bandgap that limits the reliable operation area with the silicon dioxide used as dielectric, and we have the presence of the carbon atoms. If we can just click one more time. Yeah. So for the silicon, we have the saying that the silicon to silicon dioxide interface is a God-given interface, and for the silicon carbide to silicon dioxide, we can use an analogy that it's a devil-given interface. Because for this one, we are suffering from all kinds of defects at the interface that are creating this near interface oxide traps. We have the carbon clustering that is creating several defect energy states within the bandgap. And as a result, even today, in the state-of-the-art devices outside in the market, we have 1 to 5% of bulk mobility by oxidation. Very recently at Ice Cream conference, we have heard from an industrially renowned expert, Peter Moens, that there should be a way to improve this mobility by an order of magnitude at least, so that we can talk about reaching the limits of silicon carbide technology today. If we go to the next slide, I will briefly mention why it is this worse compared to silicon. So here we see the interface state density distribution across the band gap of our semiconductors. For the silicon, we see that the levels are in the order of 10 to the 10. Whereas for the silicon carbide, for the thermal oxide, as grown thermal oxide, for the NMOS or for the PMOS, regardless, we have the defect density we have the interface state density in the range of 10 to the 13, meaning that this is a very defective interface, and we have the severe carrier trapping as well as column scattering, and as a result, we end up with a ultra low mobility. So, of course, the industry doesn't just adapt directly the thermal oxide and that's it. We had to do quite some tweaks across the decades. And today, what is commonly applied to improve the interface is nitric oxide post-oxidation treatment. Then, of course, there are several studies in the academic as well as industrial level using high temperature and post-oxidation to fix the interface density. The hydrogen post-oxidation treatment is shown to be quite an effective method with the question mark on the stability of the device. The pre-deposition anneal with the hydrogen is known to cure the surface roughness of silicon carbide when it is done at an appropriate temperature. Then, as also Michael was hinting, the plasma treatments on the surface can greatly change the behavior of device for the silicon carbide as well. And of course, when the interface of the thermal oxide to silicon carbide is this bad, one cannot stop asking himself or herself the question, how about I just deposit the layer and then I stop this oxidation of the interface? And this is the methodology that we follow in the InnoGate project. And we basically investigated deposited silicon dioxide instead of thermal grown silicon dioxide, as well as high K dielectrics. So with that, I will leave the stage to Ben to
Thank you very much. Thank you both, Michael and Sami, for the great presentations so far. I will just take and build upon basically what Michael and Sami have already said. Next slide, please, Alex. Just a little bit, and then I think we've heard a lot of background now, but just one graph, I think, which basically sums up the huge opportunity space. It's the one on the left-hand side, where we can plot specific on resistance, like a device's resistance, over the voltage rating. And then we've got two lines here. You see the silicon unipolar limit. That's basically the limit of the technology limit for devices such as Schottky diodes or MOSFETs. And you see the silicon carbide unipolar limit. And on the silicon unipolar limit, you see basically that the devices that we can measure, that are basically commercial off-the-shelf devices, they sit more or less on or even slightly below the unipolar limit. For silicon carbide, more towards the right-hand side of the graph, that is not the space. And Alex, if you just click once. So what we see here is basically a huge opportunity space in which we can think about ways to further push the technology towards its technological limit, towards the unipolar limit. And then if we look on the right-hand side, where we can also plot specific on-resistance components over technology that's currently out on the market, you see that basically the channel is a huge proportion of this. Yeah, next slide, please. I think Sami, both, and Michael have already spoken quite a lot about why thermal oxidation on silicon carbide has big advantages in terms of cost, but also long-term, you pay a price there. Long-term penalties in terms of reliability and higher losses. Next slide, please. Yeah, that's basically fine. Basically, what you end up in a thermal oxidation process with is that you generate trapped charge at the interface, limiting the effective conduction across the channel, and thereby by scattering electrons and thereby increasing resistance. Next slide, please. So the oxide interface, to summarize, is basically the majority of silicon carbide's present issues. So you have a suboptimal device efficiency because you get low channel mobilities. It has an impact on device yield. So you get a lot of devices failing when stressed instantaneously, basically straight at the beginning. So you have to bin these devices, so you have higher chip costs. And it's a source of poor reliability, because this is a fundamental device weak spot, especially during short circuit, also during cosmic rays. So you have to excessively derate these devices, meaning that you have to over-dimension them, or like use thicker oxides, or use more material than you would normally have to do. Next slide, please. So now we've talked a lot about the bottleneck, and in this project that we worked on, our aim was to reduce this and improve the channel mobility. And we did this by fundamentally changing the technology. We moved away from thermal oxidation and went to a process that uses pure chemistry, basically. You have a silicon precursor, you have an oxygen precursor, they react and they come down on the surface. You do not consume anything of the underlying semiconductor material. Next slide, please. And then we basically, I'm going to skip through this, we basically ended up fabricating devices, MOSFETs, where we could actually use these layers, atomic layer deposition, deposited layers, and then we actually wanted to find out, can we actually improve it? Can we actually, how does it compare to thermal oxidation? The next slide, please. And we can see here that when you look at key performance metrics, like the graph on the left, I'll keep it very light, basically shows you the capacitance of the device plotted over voltage. You see the graph, the black graph here, which is basically an as-deposited ALD SiO2 oxide, which is leaky, it's not great. You see on the x-axis, it's not where we want it to be, which is quite close to zero, but we can, by pre-tuning the material before we put down the oxide, we can bring it down to a very competitive state. The next slide, please. And when it comes to further key performance indicators of the interface, and we've spoken a little bit about density of interface traps. That's the graph on the right-hand side, where we have to say that this in silicon carbide is basically 2 orders of magnitudes higher. You've got a lot of defects basically present at your interface that will scatter electrons during MOSFET operation, that will increase your losses, that will decrease your yield, and that's basically bad for device performance. And you basically want to have this number as low as possible. And by applying our processes, by switching over from thermal oxidation to an ALD-based process, that gives you the flexibility also of preparing your samples in the ALD chamber before you put down the oxide. It also gives you the opportunity to anneal the oxide after you've done the oxidation. So you basically have more degrees of freedom, more degrees of control, as Michael rightly pointed out before. But we have basically managed to get a process that was very competitive. It's basically state of the art, and even exceeding that low density of interface traps. Next slide, please, Alex. Then also another thing every device engineer will ask you about when they talk about gate oxide is, yes, but how about leakage currents? How about leakage in my device? We basically also tested this, and we got a leakage current, a breakdown, which you see here at around 10 megavolt per centimeter, which is where you would expect it, maybe even a little better than what you would see with the thermal oxide. Here as well, another key performance indicator, they outperform what's currently out there. Next slide, please. And then what happens when we actually check MOSFETs? So we have a process where we basically did the ALD oxides. We applied the magic. We did something before we put down the oxide. We did an anneal afterwards, and how do they perform? And on the right-hand side, you basically see on the bottom graph that by applying an anneal here, you get a value of 55. So what does that mean, basically? It basically means that your field effect mobility is 55 centimeters squared per volt second, which is about 2.5 times higher than what you would normally expect on a thermally grown oxide. And that translates into real device improvements, into real resistance reductions. Next slide, please. And we basically demonstrated as well that these devices turn on, they behave like normal MOSFETs. Next slide, please. Now, coming back to the fundamental question, just getting a number of from 20 to 50, why do I care? It doesn't sound like a lot. Why does it actually make a difference in the real world? So if we, with the help of our PhD students, postdocs, and academia, and obviously the industry input from Hitachi Energy and Oxford Instruments, we took a model of a basic commercial off-the-shelf MOSFET, 1200 volts, a planar MOSFET, and we simulated and basically assumed, okay, we end up having a mobility of 20. What happens if we take that mobility up to 50? Next slide, please. This basically results in a reduced conduction loss, 2.5 times reduction in channel resistance. That's a lot. That means 10% total device resistance reduction. So what that basically means is that I can also switch my device faster because I hit the current levels faster because my device is less lossy. So I get a 45% increase in how fast the device basically can turn on. Next slide, please. So yes, so what to do with this? What do I do with this improvement? Just by switching over to ALD oxides, to adapting the process that we've just seen. So I could basically fix the area in my device that I've shown before, my 1200 volt device, and basically get the same product and take the total device resistance down by 10%. So this in the bottom left turns from a 12 milliohm device resistance to a 10.7 milliohm device resistance. I get the same same area dimensions, but it's just less lossy. Next slide, please. But what's actually a bit more interesting, I could try and keep the electrical parameters of my MOSFET the same, but I can now try and reduce my product area. So a 10.9% specific on resistance reduction translates into a 5.6% reduction in device area for a given on resistance. So my device is just 5% smaller, but it can still block the same voltage and it can still conduct the same current just by improving our gate oxide process. So it's a net benefit. If you could just click once, Alex, please. So that not only reduces my area, but it also reduces my device capacitances now because I've got a reduction in area. And we see that across the industry, maybe, for example, just by looking at Rome, which are a big industrial company working on silicon carbide MOSFET development. So they recently announced a change in product generation with a 40% device area reduction, and that then translated to a reduction in capacitance. And you can basically see that the device now switches a lot faster simply because I changed the areas, because my gate oxide allows me to. Next slide, please. And then it's basically a double whammy because I get to reduce my device area. The game of statistics also then applies. I basically end up having more devices, more chips on a full wafer, and then the chips are smaller, and therefore they are less likely to hit one of those killer defects. So I also improve my yield. Next, please, Alex. And that then eventually, in the end, results in a reduction in cost. Just in the example that we've seen here, I can now reduce the cost per die by 10 cents or 11. Obviously, it doesn't sound like a lot, but you have to think what were to happen if you were to scale this up. Like one 6-inch, 8-inch wafer has got thousands of these products on it. And if you can save cost per die and multiply that by 1,000 by 2,000, then you're talking about big numbers, because your wafer throughputs in a fab will be thousands of wafers every month, sometimes even every week. Next slide. And then also, this also results in improved reliability and yield from the lower density of interface traps. And that's something that especially Hitachi Energy, also Oxford Instruments, have been working on, showing, yes, it is also reliable if I switch from a thermal oxide to a deposited oxide, and I don't have to sacrifice anything in the long-term operation of my device in the field. And in terms of yield, we can also show that because it's more reliable, you can also reduce your burn-in failures related to gate oxide failures, just because you've worked on this key interface. Next slide, please. And now I think I'm not going to go through the entire conclusion, but what we've basically shown in this project between Hitachi Energy, Oxford Instruments, Plasma Technology is that ALD can represent and does represent a step change in gate dielectric engineering and performance. It gives you an improvement in terms of levels of control, an improvement in terms of resistance reduction. You get higher channel mobility. It is a better and more reliable gate oxide. And this is not just an incremental one. We think that ALD oxides are also essential for the future of high performance power electronics. And with that, I'd like to end this talk. Thank you very much for listening.
Great. I'm just going to stop sharing my screen, and I'm going to spotlight all the speakers. So yeah, fantastic. Thanks so much for running through that. Really, really interesting. Hopefully the webinar audience also found that as interesting as I did. If anybody has any questions, please feel free to add them into the chat. I'll be monitoring those. I got a couple to start off with whilst we're waiting for some to come in. So how applicable are these sort of new techniques to other wide bandgap systems, or how much can you learn from, say, these systems to then apply to, say, gallium nitride, gallium oxide, or lower TRL materials as we look to develop processes for them?
Maybe we can let Michael quickly comment on this, given the expertise that Oxford Instruments have in that area.
Yes, yeah, of course. There's a lot of applicability. What has driven the silicon nitride development we've been doing is gallium nitride. The gallium nitride market, they need nitrides at the interface to preserve the 2D electron gas and to give you better control. But then a good silicon nitride can be useful across a wide range of materials. Micro LEDs is another one that's up and coming. They will need similar control as silicon carbide and gallium nitride. When you look to gallium oxide, which is now a future wide bandgap semiconductor material, almost all of the techniques we've been talking about here on the etch and adapt are going to be applicable in some sense. The process will not look identical. You will find that there's different things you have to do to prepare the surfaces, that you might need to look at a different precursor in order to get the same quality material. But the lessons you learn are applicable across the board, because you have that toolkit, what has worked in the past, so you know what you can try and see if it gives you a similar performance benefit.
Sami, did you want to comment also?
Yes, for the different wide bandgap materials, if you talk about them, as just Michael pointed out, I mean, every material comes with its own interfaces. But the thing that I myself really like about ALD is, I mean, you can implement it on amorphous materials, you can implement on the crystalline materials. Today, we even see implementation on the 2D materials with different interlayer conditions on them. So that's the universality of this method. So with this way, I think we can clearly say that this will be applicable across different fields, different material families.
And I think it's also fair to say, I mean, ALD's got an extremely strong track record. It's not like you wouldn't see ALDs in foundries and fabs across the globe. It's got a strong presence in CMOS. A lot of the technologies completely rely on ALD to put down their oxides and their dielectrics. So it's definitely universally applicable.
Great. So we've had a couple questions come in. So what are the challenges of employing ALD techniques in scale manufacture, particularly throughput, and what solutions are there for that?
That sounds like one I should take.
Yeah.
The first thing you have to look at is what is the thickness of material you want to deposit. If you're talking beyond, say, 50 nanometers, 100 nanometers, ALD probably is not the technique for you, because it's a cyclical process. So you can make the throughput better, you can speed up the process, and that's what we are exploring. But inherently, you are going to be slower in depth rate than a chemical vapor deposition or even a physical vapor deposition technique, because you need to pulse things, and it's that cycle time that is what dominates how much you can get in your throughput. But in terms of making it applicable for those thinner materials, and most of the time when we're talking about power semiconductors, we are really talking about 5 to 20 nanometers of material, then it's a choice of your precursor and your process conditions. So in almost all instances, you can get that cycle time down to something where you can get a good process with good control that gives you somewhere in the region of the thousands wafer a month. Once you get to that, then in industry, what they're really looking at is cost of ownership. So as Ben was hinting, if you can make your die, if you can improve the yield on that, if you can get that with good throughput, the cost of ownership then starts making sense. The cost per wafer and the margins per wafer then all link up. The other challenge you always have, but this is for any process where you are depositing material, is particles. So you need to understand how dirty the process is in essence. The ideal process would not generate anything outside of what you put on the wafer. No process is like that. But what you can do is you can tailor the process so you can understand how you control those particles and understand how quickly they build up. And then you can say what the cleaning regimes have to be in order to keep that side under control. At the moment, with something like silicon carbide, the killer defect size is actually quite big. So particles is not as much of a challenge yet. It will be coming as devices shrink. So if you look in CMOS, particles are probably the main thing ALD vendors are looking at, because the killer particle size is on the order of a couple of 100 nanometers. In silicon carbide and gallium nitride at the moment, the killer defect is probably on the order of 1,000, 2,000 nanometers. So when we mature that market, that will become more of a consideration as well.
Great. Can the higher reliability of ALD gate oxides enable the use of higher gate voltages at the same device lifetime compared to thermal oxides? I guess this links into a question that I had, which was around what challenges are there going to be as you're moving towards these higher and higher voltages. So I imagine like 3.3 kV, 6.5, 10 kV, as we look down where silicon carbide's roadmap is going, what do you need to overcome to basically get there from this point of view?
Let me just quickly comment on the different voltage classes. Obviously, what we see when we go up in voltage classes, say, for example, from an EV applicable product that operates it, that's basically a 650 volt device currently, still the most commercially important one, up to 3.3 kV. The importance, obviously, of your channel resistance, like the fractional resistance contribution decreases. Then it comes down to your drift region thickness is basically the one where the device drops the biggest resistance during current conduction. Still, when it comes to reliability, the gate oxide will play a role there. Maybe that's something, given the extensive body of research that's been done at Hitachi Energy, that Sami could comment on a little bit.
Yes, sure. So if we take two materials, I mean, that doesn't have to be deposited silicon dioxide versus thermal oxide. So if we show that one of them has better reliability in terms of lifetime, that's already a good sign. we can try to operate this device at a higher gate voltage and end up with the same lifetime. I think that is what the question is asked. But we always need to keep in mind the stability of the operation. So we cannot just say that, okay, this device has better lifetime, higher lifetime, it will operate better. No, the operational stability is very important, and there it comes down to the interface treatments that we are doing there. So I don't think that we can just answer this easily without investigating it truly, that a deposited oxide will be much better in terms of operational stability and lifetime in the field use compared to thermal oxide yet. We have the signs that they can be improved, but beating a thermal oxide interface is one thing, but the bulk of the thermal oxide is another thing. Beating the thermal oxide is an extremely challenging process there, because we are talking about something that is grown for the trench devices at a temperature of 1500 Celsius. So you can imagine the purity of such a process. Interface is what stays dirty, but the bulk is very clean. So this is the thing, key thing. But of course, this is what we are working on. And as the implementation partner of the project, we are really, really looking forward to giving a go and investigate all these aspects in our chips.
We have already run over time, so I had a couple more questions, but I'm gonna hold off on them. I'll just send them to you out of interest anyway. But yeah, just finally, a massive thank you to all our speakers, so Ben, to Sami, and to Michael. Before I let everyone go, just to highlight a couple of things I've put into the chat. So we've got our annual showcase coming up in November, which is being hosted by the University of Warwick. If you're interested in attending, please do sign up. There's a link to registration of interest in the chat, and we're also looking at future webinars as well. So if there's other areas that you'd like to have webinars on or collaborate with us on, feel free to get in touch with us. But yeah, just a final thank you to everyone for attending today. I hope you found it really interesting. And yeah, again, thank you to Michael, to Sami, to Ben for a really fascinating webinar. And with that, I will let you get on with the rest of your mornings.
Cheers. Thank you very much.
Thank you very much.
Thank you.
Bye.
Bye-bye.